Today we're looking at section 2.7 notes. So today we're dealing with analyzing graphs of functions and piecewise defined functions. So this first note is a test for symmetry. So there's three tests, and what you do is, in order to test for x-axis symmetry, you replace the y with a negative y. And if you get the same exact original equation, then that relation has that symmetry. So if I do replace the y with a negative y, this is not the same thing. So that does not have x-axis symmetry. For y-axis symmetry, you replace the x with a negative x. Well, in this case, if I replace that x with a negative x, it's y equals parentheses negative x squared plus 3. And that simplifies. Negative x squared is x squared plus 3. This is the original equation, so this graph has y-axis symmetry. Origin symmetry, what that is, it looks the same right side up as upside down. You replace the x and the y with a negative x and a negative y. So in this case, this would become x squared again, but then this negative y would just look like this one here. So this graph does not have origin symmetry, only y-axis symmetry. If we looked at that, y equals x squared plus 3. It's up here. So in order to have x-axis symmetry, it would fold on itself over the x-axis. Well, this graph is only up here, so it definitely does not have x-axis symmetry. And any function cannot have x-axis symmetry. Y-axis symmetry, it folds on itself over the y-axis, and I'm seeing that happening here. And origin symmetry is if you took this and flipped it upside down, it would not look the same, because one would be a parabola up and the other one would be a parabola down. So this one only has y-axis symmetry. Let's do this equation. So absolute value of y equals x plus 1. So x-axis symmetry, replace y with negative y. And if you do, this is the absolute value of a negative y. So you would just positize that. So that would just be absolute value of y equals x plus 1. That is the original equation. So this graph does have x-axis symmetry. Y-axis symmetry, replace the x with a negative x. If you do that, this is not the same equation. It does not have y-axis symmetry. Origin symmetry, replace the x and the y with a negative x and a negative y, and simplify. Well, this thing would, after this simplified to this, this part here would be look similar to this. So this is not going to be the exact original equation, so it does not have the origin symmetry. So let's take a look at that. So absolute value. So absolute value of y equals x plus 1. So on this graph here, I'm seeing this sideways absolute value graph. I'm seeing, yes, x-axis symmetry. So this is not a function. A function cannot have x-axis symmetry. So most absolute value of y's. I'm not seeing any y-axis symmetry because I'm not seeing if you fold it over the y-axis, it folding on itself. And I'm not seeing origin symmetry because you flip this, it would, instead of a v opening right, it would be a v opening left. So this graph, absolute value of y equals x plus 1, only has x-axis symmetry, which is what I proved right there. Okay, so now we're looking at even and odd functions. So if we're talking functions, we're not going to add in x-axis symmetry because a function cannot have x-axis symmetry because it would fail the vertical line test. So functions can have y-axis symmetry, and we call that even functions, or it can have origin symmetry, and we call those odd functions. So this graph here is symmetric about the y-axis. So you can take this and fold it over itself, and this whole graph would fold right on top of it. One property of even functions is that f of negative x is equal to the f of x. And what that means is if you put in the positive or negative x value, you're going to get the same y value. So for example, a good example of an even function is fx equals x squared. And no matter what value you put in, if you put in a 2, you get 4. If you put in a negative 2, you get the same y value. So the f of the negative x is equal to the f of the x. F of 2 equals 4, f of negative 2 equals 4. So that's true for all even functions. So this has this, this 3 has this value, and this negative 3 is this value here. So odd functions, if you take your paper and you flip this upside down, it's going to look exactly the same. If you just remove these numbers, you can't tell right side up is upside down. So this graph has origin symmetry. It's an odd function. So one property of odd functions is the f of the negative x equals the negative of the f of x. What that means is if you put in the opposite sign x, you get the opposite sign y. So this graph happens. If you put in this 3, you get this number here, say 2, and if you put in the negative 3, you get the negative 2, something right around there. A good example of that is x cubed. So if you look at x cubed, if you put in the positive 2, you get a positive 8. If you change the sign, it changes the sign of the y value. So f of the negative x equals the negative of the f of x value. Okay, so how would we prove that? So, graphically, you can tell even functions symmetric about the y-axis. Odd functions look the same right side up as upside down. That's origin symmetry. Well, what about, how do we do it algebraically? What we're going to do is we're going to replace the x with a negative x and see what happens. So in this case here, if I replace every x with a negative x, I get negative x to the fourth plus negative x squared plus 1. This simplifies to x to the fourth. This simplifies to x squared plus 1. This f of negative x is the original f of x, proving that this is an even function. Even functions are symmetric about the y-axis. So let's check that out. X to the fourth plus x squared plus 1. Yep, even function. I'm symmetric about the y-axis. I'm seeing that there. Let's check the second one. Replace the x with a negative x. Well, if I do that, I get this and I get this. Negative x cubed is negative x cubed on the outside, and this would be plus x. You can factor a negative out of both terms, and there'd be negative parentheses x cubed minus x. So what that means is the f of the negative x is equal to the negative of the f of x. That's a proof that that is an odd function with origin symmetry. So again, just to recap, if f of negative x equals f of x, if you plug in the negative x and you get the same exact original, even. If you plug in the negative x and get the negative of the original, that's odd. F of negative x equals negative of the f of x. So let's check this one here, x cubed minus x. So what I'm seeing here is this nice symmetry here. So you got this value here, you're seeing some interesting numbers here. You put in the opposite sign x, you get the opposite sign y. It looks the same right side up as upside down. So this is an odd function with origin symmetry. Most functions don't have any symmetry. So like something like this, if I put in the negative x, I get this plus this. This squared is just x squared. This changes the sign, and then this doesn't. So when some things change sign, like this one, and some things don't, like this, then it's neither. It's neither even or odd. Most functions don't have any symmetry. It's just we're adding these little describers for functions. Again, a function itself is a relation that passes the vertical line test. For every x value, there's at most one y value. And now we're doing just a couple more describers, talking about even functions and odd functions. Okay. So what about a piecewise defined function? Well, what I want you to picture is, the x value is going into the function machine and getting an output. But now what happens is the x values have to make a choice. So you have to look at this part first. And the idea is like, as you're going along, all the x values that are less than 0 are going to follow this rule. And every x value that is these x values, x greater or equal to 0, is going to follow this rule. So for example, if a negative 4 is coming up to this one function, this is one piecewise defined function, negative 4 is going to follow this rule here. So if I put negative 4 into this, I get negative 4 squared is positive 16 minus 16 minus 12. So f of negative 4 is negative 12. I don't put it into both functions because this is all one functions. For some x values, it follows this rule, and for other x values, you follow this rule. So f of 4, well, 4 is going to follow this rule here. So if I put a 4 into here, I get a 2. How I graph piecewise defined functions is, let's graph the entire negative x squared plus 4. So here's the entire negative x squared plus 4. It's got x squared, it's got a reflection, which is negative x squared, and then up 4. you know, if you pick numbers 0, 4 are points, and then if you put in y is 0, you're going to go 2 or -2 is the x-intercepts. So y-intercept of 4, x-intercepts of 2 or -2 by solving that equation. So I have this graph here. Okay, so what if I didn't want the whole thing? What if I just wanted it on the interval x less than 0? And I use these little squiggly brackets here. So that's just this piece here. And then the Desmos doesn't show up, but I should have an open circle right there. So I just want this piece here. And then what if I also wanted equals square root, SQRT, of x. But I don't want the entire square root of x. I just want the square root of x function, oops, for x values greater than, so I'm going to hit the greater than, and then hit equal, and it turns it into that, 0. Oops, 0. And so it's interesting, that is the domain of it, so nothing really changed here. So that is going to be a closed dot there, since greater than or equal to. And that's going to be an open circle. So Desmos doesn't show that, but that's what it is. But this is all one function here. One domain, one range. So I have this piece here, open circle. Because we don't go, like -0.001 is going to be part of this rule here. All the way to 0, not including. And then starting at 0 is going to start here. So this is one function. It's got one domain of all real numbers. Every x value knows where to go. And then the range is going to go -infinity to infinity, because this is going to go all the way down. And this thing takes its time, but it does go all the way up, because square root of 36 is 6, 49 is 7, 64 is 8, 81 is 9, 100 is 10. It's going to keep going up, taking its time. So again, this is one function that has one domain and one range. Okay, so this one here, I'm going to kind of show you this one on the calculator too. This is called the greatest integer function, so we'll deal with that in a second here. And we'll just do these first two parts first, just to kind of see what's going on with these guys. Let me pull this up just so I can do the greatest integer, show you where that is on the calculator. I'll do this in a second. Okay, so first off, let's do the piecewise part. So again, now there's 3 rules for this piecewise. The function equals 3 for x values less than -1. So that's, here's the 3 function. Y equals 3 is a horizontal line, all horizontal, for x values less than -1. So with an open circle at x is -1. And then if I draw the 2x line, so 0, 0 here, this is the 2x line here, but I don't want the entire 2x line. I want the 2x line greater than or equal to -1, so starting here, but then less than 1. So that's going to be open circle right there. So here's these two pieces here. Okay, so now let's add in this third one. This is a new function, this greatest integer function, and I wanted to kind of show you where this is and everything on your calculator. So look, this is a different bracket called greatest integer. It's a function that comes up in this section. So I'm going to clear all this out. Go up here, let's turn our plot off. That plot should never be on if you're doing anything. Unless you're doing something with data, none of these should be highlighted. You can just go up and hit enter on it to turn it on, or go up to it, hit enter on it to turn it off. Okay, so just to kind of show you a couple things, like on the calculator, if I go math num, and then absolute value of x, and then you can either graph it, but I always hit zoom 6 when I do new graph, zoom standard window. So that's absolute value of x on the calculator. In this case, I don't want absolute value of x. I want to go math num. I want to go down to number 5 to this greatest integer function. So I'm going to do that with an x. And this function looks like this. It's a step function. Well, what does it mean? Well, let's go to the table. And this table just looks like, oh, it's 6, 6, 7, 7, 8. Was it just the line y equals x? Well, no. If I change my table, so second table set, second window, I'm going to start at 0, and I'm going to count by 0.2s and kind of see what's happening here. So I'm going to go back to the table, second table, and I'll look at 0, 2, 4, 6, 8. It's all 0 until it gets to 1, and then the output's 1. Then 1.2, 4, 6, 8. That's 1 until it gets to 2, and then it outputs 2. 2, 4, 6, 8, and then it's 3. 2, 4, 6, 8, and that's 4. So what you have is these steps where at the integer, it's equal to the integer, but then it stays the greatest previous integer. This is called the greatest integer function. It's going to stay that value until it gets to the next one. So for this one, we're starting at 1, so it's at 1. And it's going to stay 1 until you get to 2, and then it's going to jump to 2. And it's going to stay 2 until you get to 3, and it's going to jump to 3. And it's going to stay 4, and then we're not going to include 4, we're going to go less than 4, so it's going to stay open circle there, and we're going to stop it there. Okay, so if f of 2, in this case, is equal to that 2 value there from the greatest integer function, the domain is going to be negative infinity to 4, parentheses, because I'm not going to include that. And then this one has a weird range, because if you notice, the range is going to be all the way from -2 all the way up to 2, and I'm going to include every value. But then it's also, I skipped 2.1, 2.5, all that stuff, and then it's just back at 3. So how do you do that? Well, I'm just going to use the squiggly brackets to say that the number 3 by itself is also in the range. And again, I'm not going to use interval notation because it's just a single number there. So again, a couple of tough things to talk about here. Again, we have what a piecewise function is, again, following different rules at different times, but then also this greatest integer function, a new function that's on our calculator, and what it is, it's the step function, and the output is the greatest previous integer. Okay, so here is a little section just kind of describing local mins and local max, and the big takeaway is that anytime you have a little mountaintop, or a little highest, you have a y value that's the highest in a little area, we're going to call that a local max. And anyone that's the lowest in its area, we're going to call that a local min. So these are valley lows, and these are mountain peaks or mountain tops. And a little here is like there's also global, the absolute mins and maxes, and that's the overall highest and lowest on the entire graph. And that's something that we're not going to do this year. We're just going to deal with the local or relative mins and maxes. So the words local or relative mean the same thing. And also this here, when you talk about maxima, that's plural. So like a maximum is a singular, and then you wouldn't say maximums, you say maximum for the plural of maximum. So just FYI on that with these new words. And another note here, so we're always going to provide intervals of x values when we're talking about domain, increasing, decreasing, and constant intervals, and the range is going to be given the y values. And we're going to use interval notation for those. So here's just a graph just to kind of wrap some of the stuff up here. So I can fit everything in here. Everything except for concavity, we'll do that second. So this is just a graph analysis. And we're saying like, okay, what's the domain? So arrow, arrow, the domain is all real numbers, negative infinity to infinity. Lowest to highest. Range, lowest to highest. So I go all the way down -5. I have that value and up. So it's bracket -5 to infinity. X-intercepts, I see 1, 2, 3, 4 of them. A couple I have to guess at, but that's fine. So this is like -2, 0. This is 1, 0. This is like 2.8, 0. And that's maybe 4.9, 0. That's just a guess on those. And that's fine, just to recognize from a graph, if I don't have the equation, I'm just going to kind of guess at it. Y-intercept is 0, -3, right down here. So increasing and decreasing intervals, what we're going to say is as we go from left to right, a lot of people look at this like, oh, look, it's going up and up, increasing, increasing. But really, we're going to go left to right. And as we go left to right, this function is going down, and then up, and then down, and then up. So the increasing intervals are from this point to this point. So when x is -1 to 2, and then union from 4 to infinity. And you can put brackets here, here, and here if you want. That's where different books might show it differently. Our book uses parentheses, so I'm going to do that as well. But I'm not going to mark that wrong either way. So the decreasing intervals are from all the way -infinity all the way to -1. It's decreasing. And then from 2 to 4. These are, again, these we always list out the x intervals. Now constant has to be at more than one point. So some people want to consider the turning point constant, but that's not what that means. Constant would be for a certain section where you can write an interval where the y values stay the same, and there's none on this graph. Local mins and maxes, this is where you have to be very specific how you write it. You can either write it like this or like this, but you can't write the point. So for example, you can't write 2, 1 is the local max. You either have to say g of 2 equals 1, or the local max is 1 at x equals 2. The answer to that question is the y value. So you're always looking for the y value as the answer. You can just write 1 if you want to. That's actually totally fine. And then the relative mins are at -5 and -2. So -5 at x equals -1 and -2 at x equals 4. Okay, so concave up and concave down is more of like a guessing game, but if you look at this little section here, this is salad bowl up is concave up, and this is salad bowl down is concave down. Now what's interesting about concavity is if you notice this graph goes decreasing and then increasing, but it's concave up, salad bowl up the entire time. This piece of the graph goes increasing and then decreasing, but it's concave down the entire time. So those aren't, things, if you're increasing, you have to be concave up and vice versa. It can all be mixed up. And so it is kind of a guessing game. So let's look at this. If you look for this whole section right here, this is all salad bowl up, concave up in this section here. And then in this section right around here, it switches to concave down. This is salad bowl down. And then from somewhere here to here, it switches back to concave up, salad bowl up. So again, I kind of guess like right about here, this blue point here is where I see this switch from concave up to concave down. So I'm going to put that as a little pointer. And then from right about here, it switches from concave down to concave up. So it looks like the concave up is from -infinity to an x value of 0. Again, this is an interval. So we don't write that y value from the x value of -infinity to 0, and then from the x value of 3 to infinity, this graph looks concave up. And anywhere right around there is fine, but it's going to be right in that ish area, right around here. I see that switch happen, right about there. And then concave down, I'm going to say from 0 to 3. So right around here and right around there is the switch. So there's our homework there. So hopefully you had fun with these problems. I will see you next time in class. Take care, everybody.